Hi class, welcome to lesson 6-4. In this lesson we're going to be learning about some properties of some special parallelograms. Last lesson was about parallelograms and we looked at all the special properties that parallelograms possess. In this lesson we're going to look at some of the specialized parallelograms and you may be familiar with some of these. In fact, we're going to be proving and applying properties of rectangles, rhombuses, and squares. So I'm sure you're familiar with those. And we're going to use properties of rectangles, rhombuses, and squares to solve problems. So we're going to prove and apply, and we're going to use properties. Let's start off with the rectangle. So a rectangle is defined to be a quadrilateral with 4 right angles. So when we think about the definition of a rectangle, we probably think about, what automatically comes to your mind is probably like opposite sides that are equal. But the actual definition doesn't say anything about sides. It simply says 4 right angles. So they say it's a quadrilateral, meaning it has to have 4 sides, and it has to have 4 right angles. And that's the extent of the definition. But if we think about the properties of rectangles, then of parallelograms, and we said that like opposite angles were equal and opposite sides were equal. And so one of the ways we were able to prove that something was a parallelogram was to show that opposite pairs, both pairs of opposite angles were equal. Well, that actually makes a rectangle a parallelogram because both of the pairs of opposite angles are congruent. So we actually know that a rectangle is a parallelogram. It's just a very specific, much more specific kind of parallelogram. And so a rectangle will possess all of the properties of a parallelogram. So another way to say that is to say a rectangle shares all the properties of a parallelogram. So all those properties we learned about parallelograms, opposite angles congruent, opposite sides congruent. We found out that the consecutive angles added up to 180 degrees, and also that diagonals bisect each other. Well, all of those properties are true in a rectangle because a rectangle is a parallelogram. And that's exactly what the first part of this theorem, properties of a rectangle theorem, says, is if a quadrilateral is a rectangle, then it is a parallelogram. And if it's a parallelogram, that it possesses all of the properties that a parallelogram has as well. So that's actually a really powerful theorem because what it does is it links you back to all those properties of parallelograms, and you know those are all true. And that's probably where we get this idea that opposite sides of a rectangle are equal, even though it's not part of the definition. Well, due to the fact that a rectangle is a parallelogram, then we know that the diagonals bisect each other. That was one of the properties of a parallelogram. But the rectangle, being that it's a specialized kind of parallelogram, its diagonals not only bisect each other, but its diagonals are congruent. So if a parallelogram is a rectangle, then its diagonals are congruent. So they're equal in measure, along with being, that they intersect at their midpoints. So technically, if I looked at this drawing here and I knew that those diagonals were equal, and that's what this conclusion over here says, but I also know that the diagonals bisect each other, and so if they're equal and bisect, then all of these little parts are going to be equivalent. All those little pieces of the diagonal are congruent, same length. So let's take a look at an application problem. A woodworker constructs a rectangular picture frame so that JK is 57 centimeters. So let's see where JK is. So JK is right here, so that's 50 centimeters. And JL, so JL is the whole diagonal, is 86 centimeters. So here are some things they want me to find. They want me to find, well, I guess just one thing, HM. They want me to find the length of HM. Well, there's lots of things they could have asked me. And so it looks like some of this information is just a smoke screen. Because the 50 centimeter part, that doesn't tell me anything about HM. But the 86 does. Because if the diagonal JL is 86, then that means KM is also 86. And if you just take 86 and you divide by 2, because each of these is half of 86, we'd get 43. And that means that's 43 centimeters. And that's that length right here, 43 centimeters. Okay, let's go ahead and turn the page and look at some more examples. So this next question, I'm going to designate this as a you try question. And I will tell you this, that this is a rectangular gate with diagonal braces. And two things they want you to find are HJ. So I want you to find this length right up here. And another thing that they would like you to find is HK. So here's HK. They want you to find that length also. So please pause the video now and try to find HJ and HK. And when you feel pretty confident about your answer, tune back in and you can check to see how you did. All right, so thanks for giving those a try. HJ, you should have realized that opposite sides are congruent in a rectangle, so HJ would have to be the same as GK, and that's 48 inches. To find HJ, you could have found I guess you had to find HK, so you actually could have found out what GJ was by doubling this 30.8 over here, and because each of those pieces that are cut up by those diagonals intersecting are equal. And so that means that JG is 61.6, and that means HK has to be also, because the diagonals are congruent and they bisect each other. Okay, so what about the rhombus? So a rhombus is a quadrilateral with 4 congruent sides. So quadrilateral and 4 congruent sides. Now when I say congruent sides in quadrilateral, in the same breath, you probably think of the square, but to be a square, you not only have to have 4 equal sides, you'd have to have the 4 right angles as well. And so a rhombus just has the equal sides. And this is a picture of what a typical rhombus looks like. Now it turns out that a rhombus is also a specialized kind of parallelogram. And we can tell that because if we know that opposite sides in a parallelogram have to be equal, and that makes it a parallelogram, then we know that a rhombus would have to be a parallelogram because not only are opposite sides equal, they're all equal. So it kind of meets that criteria, the conditions to be a parallelogram. And so a rhombus will share all of the properties of a parallelogram. So this rhombus will have everything that that parallelogram has, plus some additional things that we're going to look at in the properties of a rhombus theorem. So the first part of this theorem says if a quadrilateral is a rhombus, then it is a parallelogram, which is what we just talked about. So that means we get all of these properties of a parallelogram for free in the rhombus. So the rhombus has all those things plus these extra things. If a parallelogram is a rhombus, then its diagonals are perpendicular. So remember the diagonals of the rectangle were equal. Well, the parallelogram has its own special characteristics of the diagonals. They bisect each other, being that it's a parallelogram, but they're perpendicular. And what that means is right here in the center where these diagonals intersect, that's a right angle. So that's really important. And that's what the statement says here is the diagonals are perpendicular. They make 90-degree angles there in the center. And that means that all of those angles there in the center are 90 degrees. And finally, if a parallelogram is a rhombus, then each diagonal bisects a pair of opposite angles. And essentially what that means is this, that each of these diagonals here, AC and BD, are actually angle bisectors. So the diagonals bisect angles in the rhombus. So these all these angles that are formed here at those corners or vertices all are bisected by those diagonals. So I could say they are both bisectors of the angles. Let's go ahead and turn the page and let's apply some of these theorems. So I'm told in this first example that TVWX is a rhombus. So this figure is a rhombus, and they want me to find some of these measurements. And so I'm going to go ahead and highlight the first one that I'm asked to find, and that first one is TV. So here's TV. I want to find that length. Well, there's no label at all on that side. So I might think I'm out of luck, but if you look at the other two sides, which I know all these sides have to be equal, so I have this side and this side, and they are both labeled, and one of them is labeled as 3b plus 4, and the other is 13b minus 9, and what I actually know to be true about a rhombus is all of these sides have to be equal. So what I could do is just find out one of the other sides by knowing what b is, and I can find that by solving this equation. 3b plus 4 equals 13b minus 9. So I can go ahead and solve this. Once I find that, I can find the measure of either xt or wv, and then that'll be the same thing as tv. So I'm going to solve this by first subtracting 3b. Then I have 4 equals 10b minus 9. I can add 9 to both sides. And that leaves me with 13 is equal to 10b. And now all I have to do is divide by 10. And so the b value is 13 divided by 10, which is 1 point. Well, what does that mean about TV? That means that TV must be the same as xt and wv, so I can use either one of those and substitute b in. So I'm going to go ahead and put it in the one that's xt, and it's going to be the same thing. So actually I should technically say that this is the length of xt, and so it's going to be 3 times that value I just found for b, which is 1.3, plus 4. 3 times 1.3 is 3.9, and then if I add 4 to that, I get 7.9. So that means that TV will also have to be 7.9. All of these sides are 7.9. This one's 7.9. All 4 of them are 7.9. So next I want to find the measure of angle VTZ. So let's see where VTZ is. That's this little tiny angle. Let's see if I can zoom in here. It's a little angle right here. So I want to find that angle. Well, first of all, I do know that the diagonals are bisected by these, or they bisect the angles. So this line right here, this actually bisects this angle, and on one side of that bisector is the angle I'm looking for. So that means that both of these are the same measure. This angle over here that I'm trying to find, and this one over here. Well, the one on the other side has a label of 5a minus 5. So I could find that angle, which is xtz, and it would be the same. So I could say, well, I'm going to find, I know that VTZ, that angle, is equal to angle XTZ. So I'm going to find the measure of this XTZ. Well, that means I need to know what A is. Well, the only place else I see angle that has A on it is right here, and it's not labeled for the angle that's next to this one. It's actually labeled at that angle in the middle, which hopefully you remember is a 90-degree angle, and that's because the diagonals of a rhombus are always perpendicular. And so what I could do is just say that that angle, which is 14a plus 20, is equal to 90 degrees. And now I can just solve that. So I'd have to subtract 20 from both sides. That leaves me with 14a is equal to 70, and then divide both sides by 14, and that's 5. So that means a is equal to 5, and now I can plug that in to find the measure of angle XTZ. So, and that angle is labeled as 5 times a. Well, a is 5, and then minus 5. That's a lot of 5s. 5 times 5 minus 5. Well, 5 times 5 is 25, minus 5 is 20. So that angle is 20 degrees. And so is the angle on the other side, where it's labeled with the 5a minus 5. So actually, if I wanted to know that whole angle, angle XTV, it actually would be 40 degrees. Okay, so before we start looking at the next example, example C and D, I want to clarify the drawing just a little bit. Well, first of all, the labels on these angles, they sort of look like they're floating in the air. B plus 3, and B plus 3 actually goes with angle GCD. So that's this angle right here, GCD. This whole angle right here is B plus 3. And then angle CDF. So CDF, this angle goes with that 6b minus 40. So that's this angle right there, and this one goes with that whole angle right there. So, and then additionally, they gave us some side descriptions of the side lengths. They said that this one is 3a plus 17 and this one's 5a. So let's go ahead and look through this example. The first question wants me to find CD. Well, CD is one of the sides. It's going to be the same as all the other three sides because in a parallelogram, in a rhombus, all the sides are equal. So what we could do is, since they're all equal, we could actually just set the two that we know, which are 5a and 3a plus 17. We can actually set those equal to each other, and we can solve for a. So I'm going to subtract 3a, and then we're left with 2a equals 17, and that means a must be 8.5. Well, now to find the length of CD, I know that CD is equal to CG, so I'm just going to find CG and they'll be equal. So that means it's going to be the same as 5 times 8.5. And that's... Now the next one wants me to find the measure of GCH. So GCH is right here. Now this one question is going to require us to use quite a few properties of both specifically the ones that are related to rhombuses, but also the ones that are related to parallelograms. So first of all, I got to use the labels that they've given me for some of the angles. So they've told me that this entire angle here on this end is b plus 3. So I know that's this angle down here. And then the one next to it is 6b minus 40. Well, remember back when we studied parallelograms, we said that consecutive angles, which this is what these are, I mean, I've got this angle right here and this angle right here, they are consecutive angles in a parallelogram. And we said that consecutive angles must be supplementary. So that actually means that if I add those two angles up, they should equal 180 degrees. So that's what I'm going to do. I'm going to add them up, set them equal to 180 and find B, and then I can work my way backwards to find that angle that they want. So when I add my like terms together, I have 7B minus 37 equals 180. That means I have to add 37 to both sides, and that gives me a 7B is equal to 217. So then if I divide both sides by 7, then, so I'm running out of space, that means B has to be 31. Well, now I have all the information I need to find the angle. So actually I can find the entire angle that's here at the vertice C. So I can find the measure of angle GCD, but then I can take that and divide it by 2, and that'll give me the measure of that angle that's highlighted, because remember the diagonals are bisected by those, or bisecting those angles at the ends. So let's see, GCD would be what I just found, 31 plus 3, because it's B plus 3, and that's 34. So if I divide that by 2, 34 divided by 2 is 17. So 17 degrees is the measure of that angle right over there. That means the whole angle must be 34, but each of the parts on either side of that diagonal are going to be 17 degrees. So let's go ahead and turn the page. So the final kind of special parallelogram we're going to be studying is the most specific kind of parallelogram. It's actually the most specific kind of quadrilateral. So a square is a quadrilateral with 4 right angles and 4 congruent sides. So it's like we're merging together the rectangle and the rhombus. The rhombus had the 4 equal sides. The rectangle had the 4 right angles. And we kind of put those all together, and we got the most specific kind of quadrilateral, which is the square. And of course, that means that the square will also have to have all of the properties of a parallelogram, but it actually has all the properties of a rhombus and a rectangle as well. But not only does it have all the properties of the rectangle and of the rhombus and also of the parallelogram, but it actually has all the properties of all quadrilaterals. So that should actually cross out the 8, should say all quadrilaterals. even some of the quadrilaterals we haven't actually studied yet. In a future lesson, we'll be talking about what are called kites, and we'll talk about trapezoids. And anything that we learn about any kind of quadrilateral whatsoever, all of those properties will also hold for a square. And I think what will really help you understand why the square has all the properties of every kind of quadrilateral, I think it's really helpful to look at what's called the hierarchy of quadrilaterals. So hierarchy is kind of like a family tree, and it basically shows the relationships and how things are related to each other, and those figures that share properties, kind of like in a family tree. Families, people in families, they share traits, they share genetic makeup. And so, like for instance, my children actually have all of my genetic DNA along with my husband's as well. And in fact, they even have genetic DNA from all of their biological grandparents and great-grandparents and great-great-grandparents, because those things are all passed down through the generations to direct ancestors and beyond. And so we can kind of think about all the quadrilaterals and how they're organized in a family tree or a hierarchy. So in general, quadrilateral means 4 equal sides. And so we're starting here at the top with the quadrilateral. So here's the quadrilateral right there, quadrilateral. And so then one type of quadrilateral, which we will study, and we'll talk more about those in the next lesson, are the kites. So that's one of the families, is the kite family. And also the trapezoid family. That's another separate little category here. So the trapezoid family, to be a trapezoid, a figure must have at least one pair of parallel sides. So if we wanted to go a little beyond that, we said, well, what about if not only did they have one pair of parallel sides, but they actually had 2 pair of parallel sides? That would make the parallelogram. And so that actually, there's a connection here where if you took the trapezoid, and not only did it have, and we'll learn about that definition here in the next lesson, that it's at least one pair of parallel sides. So if not only just one pair of sides was parallel, but both pair of sides are parallel, that would make it a parallelogram. So I've highlighted in purple all the figures that are parallelograms. So there's the generic basic parallelogram, the rhombus that we just looked at today, which has the 4 equal sides, which makes it a parallelogram, the rectangle, which has the 4 right angles, and the square that has all of those properties, 4 equal sides and 4 right angles. But these other figures that we haven't talked about yet, the kite, the trapezoid, the isosceles trapezoid. So the figures that are connected to those things below will have all the properties of those things above. So in other words, like the kites. So if I had something and it was a kite, and a kite we'll learn is a quadrilateral with 2 pair of consecutive sides that are equal. So that means sides that are next to each other rather than opposite sides like the parallelogram has. So if I kind of took that sort of to an extreme and said not only is there 2 pair of consecutive sides equal, what if they're all equal? Well, that actually leads to a rhombus. So a rhombus is actually also a kite. So it has all the properties of a kite. And if we went even further than that, and not only did we have a figure with consecutive sides equal, and then maybe even all the sides are equal, but it could also even have right angles. That would make it a square. So not only is a square a rhombus and a parallelogram, it's also a kite. So the square will have all of the properties of a rhombus, of a parallelogram, of a kite on that side, but it'll also have all the properties of a rectangle on the other side, because it also clearly meets the definition of rectangle. It's got 4 right angles. And so not only does the square have the parallelogram, the rhombus, the kite's properties, it also gets the rectangle's properties, and anything that would also be in that family above it. So also isosceles trapezoid, which is a trapezoid with base angles equal and the non-bases are equal, and then the base angles are equal. So like these angles and these angles would be congruent up here to each other. And so a square would actually have all the properties of an isosceles trapezoid. So when we learn those properties, they will hold for a square. And a trapezoid. Trapezoid has a pair of just one, at least one pair of parallel sides, and so anything that's true of a trapezoid will be true of a square as well. So knowing these relationships and knowing how all these things connect to each other will allow us to get more properties out of each figure as we go down through the family tree, because anything that is below something that's directly linked to above will have the same properties. So for instance, a rectangle is linked to isosceles trapezoid. Anything we learn about an isosceles trapezoid will hold for a rectangle, and if it holds for a rectangle, it will have to hold for a square. So the reasoning goes down the family tree. Okay, so every square is a rectangle. Not every rectangle is a square. Every square is a rhombus, but not every rhombus is a square. Every square is a kite, but not every kite is a square, and so on. So that logic, it's if you reason down the family tree, then it's not true. But if you're reasoning up the family tree, so is a square a parallelogram? Yes. Is every parallelogram a square? No. And so that's kind of how the family tree works. Let's go ahead and turn the page. All right, so let's take a look at some proofs involving these properties of special parallelograms. So in this first example, we are asked to prove that RQ is congruent to RS. So I want to prove that this segment right here is congruent to this segment on the other side here. So if we look through, just kind of scope out this proof, and the statements are already provided, we just have to come up with the reasons. I can see that along the way I'm going to be proving that these triangles are congruent, and the triangles that I'm going to be proving are congruent are PQR, that triangle, and this triangle, SPR. So I want to prove those triangles are congruent. So I know to do that, I need to know that 3 parts of one triangle are congruent to 3 parts of the other. And so I'm trying to satisfy one of our shortcuts. So let's take a look at the first statement beyond the given. So first of all, they told me that PQTS, that's this little thing in here with all the marked sides equal, that is a rhombus. So it shows me that all these little segments are equal in there. So we've got the rhombus that's contained within those 2 triangles. And then it says that PT bisects angle QPS. So that means here's QPS right here on this end, and it's saying that that PT, which you could also look at it as if it were PR, that would be the longer segment, bisects that angle. Well, we know that because we know that the diagonals of a rhombus bisect opposite angles. So I might write like this, rhombus diagonals are angle bisectors. That would be kind of the shortest way of saying that. So then they went on to say, well, then that means angle QPR, so QPR, this little angle right there, is congruent to angle SPR. And I know that that reason is because we know that that's a bisector that goes through it, which we just stated in the prior line. So that's going to be the definition of angle bisector. Next, they go on to say that side PQ is congruent to side PS. Well, I've already got those marked. Those were actually marked on the drawing to begin with. But the reason why that was true is because that figure was a rhombus. So the reason why is its definition of rhombus. By definition, the 4 sides of a rhombus are congruent. And then they go on to say that PR is congruent to PR. So if I marked that, that means this side here in the center, and it's saying it's congruent to itself. And we know anytime we say something is congruent to itself, that that is the reflexive property. And now you can see these markings. So if I erased actually the ones that aren't really necessary to those triangles, and just look at the markings we have here, notice that we have 2 sides and the angle between them. And so I know that those triangles are congruent by the side angle side congruence. And then now I can finally say what I want to prove, which is that these 2 segments are congruent. And that's because they are corresponding parts of congruent triangles. So CPCTC. Well, we're going to make this next proof an in-class you-try question. And so that actually brings us to the end of the lesson. So I'm going to see you in class.